All right, so last class period, we had looked at several different mechanisms for enzyme inhibition. And Riley had brought up this question, and I wanted to revisit that, and that was, you had asked, is there any advantage to an uncompetitive inhibitor? Okay, that's what you had brought up. And I don't necessarily know that there's an advantage to that. Again, it's just a different mechanism of inhibition, okay? So different inhibitors do different things. So I think there's just, you're just looking at it from different perspectives. So I'm gonna come back and look at the uncompetitive inhibition model in the fact that we were discussing whether or not the product formed at all. And I discovered that apparently this doesn't happen, so that you actually don't get the catalyzed reaction actually occurring at all, that it actually inhibits KCAT. So that's very fascinating, okay? Now, here's the thing, is that if you do have an uncompetitive inhibitor, and the book gives you methotrexate as that example, right? The patient, and my son actually was prescribed methotrexate for his condition. We didn't have to end up using it. The patient would still have to receive the therapy and continue to receive the therapy. Why? Why?
Does your body become dependent on it?
No?
This is uncompetitive, right?
Yeah, it's an uncompetitive inhibitor. So why if it binds to the enzyme substrate complex and it prevents KCAT, it prevents that process from happening, you don't get product formation, there's no chemistry happening, no reaction, why do you have to keep taking it?
Is it because it will eventually degrade and then you will get enzyme product?
Your body's gonna process this because this is a reversible, it's not an irreversible inhibitor, right? If it was irreversible, it would just build up until it binds to all the enzyme, right? And then your body would not have use of that enzyme anymore, right? So you're still gonna process this, it's still going to come out of your body because it's reversible. But the mode for which it binds is simply just uncompetitive, okay? Now your book actually gives you other examples of other drugs that undergo mixed inhibition. And I do think mixed inhibition actually has an advantage. Why do you think it has an advantage? Just look at the model I posted for you.
It can start anywhere, like at any point in the chain.
Not really anywhere. What doesn't it bind to? What's S?
Substrate.
The substrate. It doesn't bind to the substrate, but it does bind to the freely bound enzyme and the enzyme substrate complex together. So I would consider that a strategic advantage for a drug, right? Where it could combine to either. So if there is an advantage within a certain inhibition model, I would say that would be an advantage. It's a more flexible type inhibitor. Does that make sense? Yes, no, maybe so. Let's look at some of the ones that the book lists that are mixed inhibitors. And let's see. Example of mixed inhibitors include the approved AIDS treatment, nevirapine, as well as several protein kinase inhibitors currently in clinical trials for cancer. So we're talking serious therapies here. And if they can be flexible enough to bind in different manners and inhibit in different parts of the cycle, then that should be a strategic advantage for that particular therapy. Okay, I just wanted to kind of clarify that before we move on. I said we were wrapping up chapter 8 last class period, but we will definitely do that this class period. And let's talk about regulation of enzyme activity, okay? The book gives you an example of this type of what they call a metabolic assembly line, where you have different enzymes that are involved in different processes to produce different products. A to B, C, D, and then on to E. What would happen in your body if product E began to build up and build up? What might actually happen?
Your body might stop making product.
Okay, so.
Or some would stop it somewhere along the line.
Or would stop it somewhere along the line, right? You have to think about this. If product A builds up, or product E builds up, and the machinery, enzyme 1, 2, and 3, continue to do what they were supposed to be doing, then E would just keep building up and building up, right? There would be no way to slow this entire process down. So this is feedback inhibition, okay? Whereas product E may inhibit the enzyme for the A to B process. Maybe it inhibits the B to C or the C to D, right? And slows this entire process down. And this often happens from an enzyme or excuse me, a substrate that's produced further down the line. I think this is a very elegant system. I mean, it's really amazing how this is, how this works. Do you think this could have undesired effects on metabolism if this didn't take place? Yeah, absolutely. I mean, it would literally be like an assembly line of vehicles, and you've produced a whole bunch of engines, but you have no frames to put them in, right? And they're just literally sitting around. Look at all the major auto manufacturers right now. What are they waiting on?
Chips.
They're waiting on chips. Have you seen the pictures of the parking lots with all the new vehicles sitting in them because they don't have chips?
Do what now? What happened?
Yeah. So there's parking lots and parking lots full of vehicles that have been produced, but they don't have computer chips in them. And that is literally because of what?
The cost of oil right now?
No?
No, it's something with the way that the chips are being produced that they can't get in.
Sure, but it's a break in the assembly line essentially, right? There's probably not enough workers to make the chips and so forth. And then you get this backup or backlog of vehicles that have been produced. So feedback inhibition or feedback control prevents this type of scenario from happening within a metabolic cycle. Okay, we had previously mentioned the catalytic process in glycolysis, where glucose is converted to G6P or glucose 6-phosphate, and this is catalyzed by hexokinase in the presence of ATP and ADP. And we had looked at this previously, and we had seen how this took place. But G6P is one of those inhibitors of hexokinase. And what's really fascinating about this, and I had mentioned that when you had brought up uncompetitive inhibition, but what I didn't know, and we knew that this was involved in feedback control, but what I didn't know is that G6P is both a competitive inhibitor and an uncompetitive inhibitor, both. And this is critical for metabolic regulation. So both inhibition and activation of enzymes are essential to regulate metabolism. So let's real quick go back and look at the competitive model. So remember, the competitive model is the one that utilizes the inhibitor at the active site of the enzyme. And then the uncompetitive is the one that we just looked at. Now that's with two substrates, there's with one substrate, where the inhibitor binds on a separate site on the enzyme surface and prevents the catalyzed process to form the product. Any questions on that? Okay. So G6P is classified as what I would call a mixed inhibitor because it can do both, okay? It's a mixed inhibitor of hexokinase. It can inhibit both the enzyme, the active site, or the enzyme substrate complex. But what about more complicated regulation mechanisms? What if you had something like that? Okay. What if product G was building up?
Inhibit product D.
Okay, so it could inhibit the production of D by inhibiting the enzyme that converts C to D. It could, right?
Mm-hmm.
Or G and N both could inhibit A and B, right? And shut the entire process down.
My understanding is it never would ever shut the whole thing down. Cause you can never, it's more like, what we learned in fundamentals is it's more like, it increases and then it will decrease in concentration, and it increases and decreases in a narrow range.
That's right, yeah, because you never would want to shut the entire process down, right? That would be, again, like shutting an entire factory down. You're not gonna be producing vehicles anymore, right? Versus slowing it down, allowing for them to catch up, produce computer chips, right? They're not just gonna continue to produce automobiles and just put them out on the parking lots for no one to buy, right? What would happen? They'd just be sitting out there exposed to the elements, right? Hail and rust and everything else. So, yes, they are gonna just simply slow down. They're not gonna completely shut down the process. So an example of this type is DNA synthesis. The synthesis of purine and pyrimidine bases. DNA needs to synthesize both of these in fairly equal amounts, right? And there are plenty of opportunities for this same type of feedback control in which production occurs. So as I stated earlier, enzyme inhibition and activation is essential for metabolic processes. And this is where we come into allosteric control of enzymes and how this process occurs. Your book talks about homoallostery and heteroallostery. I would like for you to get into your groups and discuss both homoallostery and heteroallostery. And then we're going to look at the allosteric regulation of ATCase, which is here. This particular allosteric regulation example is in your book, and it is on page 264. If you have not read that, you should take time to read that. And then I want you to go through the case study on that this week. And then on Friday, we will discuss this particular case study as well. We will have a guest visitor in here on Friday, which is going to be Nathan Roberts. Nathan's just going to be observing the class. Nathan is the department, or not, he is the department chair, I think, of agriculture, but he's also the division chair, and he's just going to simply be observing our class before the end of the semester. Okay? So please do your due diligence on going through the case study this week. And then on Friday, we will discuss that and go through the questions of the case study and take a look at that. Okay? All right, go ahead and break into your groups. I will pass out the case study.
Are you just wanting us to talk about it or actually write it down in our group? Didn't hear me. Hey, Dr. Long, do you want us to write these down or just talk about it?
I would probably write the definitions of both of those down.
More on talking.
I would if I could.
Got it.
I used to know it.
Which one you got?
That's like, I think
I
we
got
were mine
both.
too in a different spot.
I got hetero.
I got both.
Or you could talk about, or you could just talk about what a homosteric, or what a homoallosteric effector would be, or a heteroallosteric effector.
Like allosteric binding is like whenever things, like if an enzyme binds, if an enzyme binds to another enzyme,
So
site B can
homoallosteric
change site A.
is the
So
substrate
if you alter it by binding to it, but not, it's not like it's blocking it.
So the active site and regulatory site are the same. Heteroallosteric is regulation of allosteric enzyme on molecule other than the substrate. Well, that's quite interesting.
What's your birthday?
What?
Who's
So
long?
it's me.
Basically, without the other definition
Back to
is,
paper tomorrow. Thank you.
all these different apps. All these negative apps.
I think it's the so it's what's coming back to emotion is
Nice.
Isn't Jesus already resurrected?
Did he keep
I thought he was already back. I thought everybody been knew.
Not for the Eastern Orthodox people, theirs isn't too high. Almost even harder.
So heteroallosteric
Service on the
dysregulation of the allosteric enzyme
Jesus is just
by
chilling.
molecule
Guys,
other
really?
He's going to lose new
I saw a
concepts.
TikTok.
allosteric
It
enzymes.
it had somebody leaning
A
out the corner. It was
molecule
like
other than the
Jesus
substrate.
after rising from the dead on his way to bottomless mimosas. Oh, it was just a TikTok.
Oh, okay, so I kinda like.
So
like
you are,
regulators, but-
yeah, you are gonna go through, you're gonna go through your case study,
Homoallosteric.
read about it in the book, and then answer the questions at the end of the case study.
We need one more.
You need one more? Okay.
Oh, wait, I have two. I
Come
gave it
on,
to
we
him.
got it.
Okay, you got two.
So homoallosteric is the substrate-induced regulation of allosteric enzymes. So the active site and the regulatory site are the same. Heteroallosterity is regulation of allosteric enzymes by molecule other than the substrate.
The first one is also, the first one, homo is regulated by the substrate.
Cheese.
So the other one.
My current favorite is the one that I just showed you, the girl chicken.
Yes, that's Daisy.
Did it say how it or like what?
What's my name?
What?
According to Bill.
Examples of homoallosteric.
Okay, what else are we supposed to find? Homo and hetero.
Homo are the same, hetero are the different binding, the active site and the.
Just
substrate.
take a few more moments and discuss that with your groups, and then I'll ask you questions about homoallosteric regulation and heteroallosteric regulation.
Does everyone understand these things? That's what I just started.
Did we all go to cram.com? Maybe, probably. Is it the first one that popped up on Google?
Okay, so,
I've got bars and stuff if you need anything.
okay, so this is another definition. Homoallosteric enzymes are enzymes that have multiple binding sites for substrates and exhibit cooperative binding. They adopt a different shape once the substrate is developed. An example would be hemoglobin. Homohemoglobin.
I don't know, that's a good question.
How does that work?
What's the other thing, enzyme inhibition act?
Heteroallosteric is like exhibit cooperative substrate.
Although my
binding
first
binding
page is
enzyme
like
is
just
the binding
frustrating.
enzyme. An example is
I know, I just got them like, this is depressing.
What is it? What do y'all hate me there about?
Bounded to
What
an
else were we supposed
allosteric
to
lead
discuss?
order.
Something about this business.
So like a lead example.
I've never
of
known
that
this.
is
T
based on
state,
okay.
T state, less than.
That's oftentimes an allosteric.
They're now playing the snake game.
That would be a heteroallosteric.
today, bro. I felt like I was.
Ooh, I think I found
My
it.
record,
ATP.
my record's 120 on here.
And ATP and AMP.
Please tell me he's playing that on like math games or something.
I would be, but put it on the Google one.
Yeah, the Google one only works at work, cause they have.
Cause they have blocks.
It's touchscreen, you keep touching things.
Homoallosteric is more
Different, y'all.
Cool math dude.
Let's see.
I mean, like, I'm not abnormally bored.
Okay, Papa's Pizzeria.
I'm in here, I go to that.
Walk up and.
Okay, anyways,
Wait,
so,
Papa's
what
Pizzeria
else do we need?
specifically, like,
What else do we need?
all of the cupcakeria, the cupcakeria.
What is she doing? Okay.
My favorite is the cupcakeria, and I stand by that choice.
Hemoglobin.
All right, Abigail, what did your group come up with? So homoallosteric or homoallosteric regulators.
Homoallosteric is the substrate-induced regulation of allosteric enzymes. So active site and regulatory site are the same.
Okay, so anyone else? Anyone else want to add to that? What's that?
That would usually inhibit the enzyme from activating rather than activating the enzyme.
Okay. Anyone else? No, that's about it. That's about it?
Like our definition was.
Or did you
that
want the
active
heteroallosteric too?
No, not yet, not yet. Your book talks about cooperative binding. Okay, what are they talking about?
We're on homo or hetero right now.
Homo,
Let's do the same.
cooperative.
They gotta cooperate.
They work together.
So what's cooperating?